Today we will analyze the response of an RC circuit when the input is a bipolar voltage pulse train. Consider an RC circuit. We have resistor equal to 1 kilo ohms, capacitor is 1 microfarad. Input voltage is a square pulse with height equal to 5 volts. On time is 5 milliseconds and off time is 5 milliseconds. For a bipolar pulse train, the height would swing between plus 5 volts and minus 5 volts. Plus 5 volts during on time and minus 5 volts during off time. Now between 0 to 5 milliseconds, the input voltage is constant 5 volts and the capacitor starts charging, and the charging equation can be given as follows. TR here is the real time. And at 5 milliseconds, the capacitor's voltage would have charged to 4.99 volts. Now between 5 to 10 milliseconds, the input voltage is constant minus 5 volts. During 0 to 5 milliseconds, the capacitor would have charged to 4.99 volts. Now when minus 5 volts is available, the capacitor also acts like voltage source. So by using superposition theorem, we can calculate the voltage across capacitor. Now here the capacitor during 0 to 5 milliseconds would have charged to 4.99 volts. Now we know that current flows from higher potential to lower potential. Hence we are taking out charges from the capacitor. So the capacitor starts discharging. This is when we are considering 4.99 volt source to be active. Now considering input voltage source to be active, the capacitor starts charging. Now on adding these two equations, we get Vc of t is equal to V in into 1 minus e to the power minus of Tr minus T start. T start here translates to the starting point of the change in the voltage level, but divided by Rc plus Vc of 5 milliseconds, which is 4.99 volts, into e to the power minus of Tr minus T start by Rc. Now this term here is the capacitor's discharging term, and this term here is the capacitor's charging term. Now let's look at the voltage across resistor. Now from KVL we know that Vin is equal to VR plus Vc. On substituting Vc in this equation, we get VR to be equal to Vin into e to the power minus of Tr by Rc. Now similarly, when the input is minus 5 volts, the Vc equation can be taken as follows as derived previously, and on plugging this equation here, we get VR's equation. Now let's see how the capacitor's voltage looks like between 0 to 5 milliseconds. If we consider 5 different time steps within this on time when the input voltage is 5 volts and calculate the voltage across the capacitor using this equation, we get the following value, and on plotting these value we can see that the voltage across capacitor is exponentially increasing during 0 to 5 milliseconds. And between 5.1 milliseconds to 10 milliseconds, as soon as the input voltage flips to minus 5 volts, the voltage across capacitor can be calculated using this equation. And on plotting this, we can see that when the input voltage flips to minus 5 volts after 5 milliseconds, the capacitor begins exponentially charging towards new steady state value of minus 5 volts while effectively discharging from its previous charge level of plus 5 volts. Now to capture the precise charging and discharging profile of voltage across capacitor, voltage across resistor and the current flowing through the circuit, the calculation is repeated in Excel with more finer time intervals of 200 microseconds. Let's look at that. This is the input that we are feeding to the RC circuit. The on time is equal to off time, which is equal to 5 milliseconds. Now I am using on time when the input is 5 volts and off time for input equal to minus 5 volts. It can be considered as T1 and T2 as well instead of on time and off time. From 0 to 5 milliseconds, the charging equation is considered and the voltage across capacitor is calculated using the equation Vin into 1 minus e to the power minus Tr, which is the real time, divided by Rc. We can see that the voltage across the capacitor is exponentially increasing during on time when the input is 5 volts, and during off time it is exponentially decreasing. Now the voltage across the resistor can be calculated during on time using the equation Vin into e to the power minus T real by Rc. And during on time, the voltage across resistor starts from plus 5 volts and decreases exponentially as the capacitor charges during on time. And when the input is minus 5 volts, VR also starts from minus 5 volts and increases exponentially towards 0. Now the current flowing through the circuit will be same because R and C are in series, and the current flowing through the circuit can be calculated using the equation VR by R. And on plotting this, we can see that this graph looks similar to VR because it is calculated using the equation VR by R. On summarizing the voltage across resistor, when the input voltage is 5 volts and when the input voltage is minus 5 volts, we can see that when the input voltage is plus 5 volts, VR equation is this. When the input voltage is plus 5 volts, VR can be calculated using this equation. And when the input is minus 5 volts, we can calculate the voltage across resistor using this equation. And on plotting this, like we observed, it starts from plus 5 volts and it decreases exponentially to 0. And during the time when input voltage is minus 5 volts, it starts from negative 5 and reaches 0 volts. Now the current flowing through the circuit is equal to VR by R as discussed previously. Now let's consider a case where T on is much greater than T off. T on here is 3 milliseconds, T off is 2 milliseconds. Now during on period, the voltage across capacitor and resistor can be calculated using the equation given. During off period, the input voltage is minus 5 volts, and using superposition theorem that we discussed previously, the voltage across capacitor and resistor can be calculated. T start here translates to the starting point of the change in the voltage level, and in this case it will be 3 milliseconds. Now up to 3 milliseconds, the input voltage will be 5 volts. But after 3 milliseconds, the input voltage across capacitor is calculated using the equation Vc of t is equal to Vin into 1 minus e to the power minus t of Tr minus t start by Rc plus Vc of 3 milliseconds into e to the power minus Tr minus t start by Rc. And on plotting this, we can see that during on period, it exponentially increases, and during off period, it exponentially charges towards minus 5 volts. Now similarly, to calculate the voltage across the resistor, for 0 to 3 milliseconds, the input voltage 5 volts is available. Hence, we use the equation VR of t is equal to V in into e to the power minus t by R, Tr by Rc. And on plotting this, we can see the behavior during 0 to 3 milliseconds. And after 3 milliseconds, the input voltage is minus 5 volts. And on using this equation, we get the following values. And on plotting this, we can see the nature of the voltage across resistor. Now since R and C are in series, the same current flows through the circuit and can be calculated using VR by R. Now here in the Excel, the on time is 3 milliseconds and off time is 2 milliseconds. On time is 3 milliseconds and off time is 2 milliseconds. The calculations here in the Excel are made considering 200 microseconds time step. Now we can see how input voltage, which has on time is 3 milliseconds and off time is 2 milliseconds, has transformed across capacitor, resistor, and how the current flowing through the circuit looks like. These values are calculated using the equation that we previously discussed for the case where T on is much greater than T off. Let's consider a case where T on is much lesser than T off. T on here is 1 milliseconds and T off is 4 milliseconds. Now during on period, the voltage across capacitor and resistor can be calculated using the following equation. During off period, the input voltage flips to minus 5 volts and voltage across capacitor and resistor can be calculated using the given equation. Now up to 1 milliseconds, the voltage across capacitor can be calculated using this equation, and after 1 milliseconds, when the input flips to minus 5 volt, the voltage across capacitor can be calculated using the following equation. On plotting these values, we can observe the voltage across capacitor. Similarly, for voltage across resistor, from 0 to 1 milliseconds, it can be calculated using the following equation. After 1 milliseconds, the voltage across resistor can be calculated using the given equation, and on plotting this, we can look at the behavior of voltage across resistor. Now since R and C are in series, same current flows through the circuit, and the current flowing through the circuit can be calculated using the equation VR by R. On time is 1 milliseconds and off time is 4 milliseconds. The calculations here in the Excel are made considering 200 microseconds time step. We can see how the input voltage has transformed across capacitor, resistor, and how the current flowing through the circuit looks like when T on is much lesser than T off. and the values here for the voltage across resistor, capacitor and current flowing through the circuit are calculated using the equation shown earlier. Here we have considered the case where on time is equal to off time is equal to 5 milliseconds. Now on simulating this, we can see that the capacitor's voltage exponentially charges towards the input voltage during on period and exponentially charges towards minus 5 volts while discharging from its previously charged level of 5 volts. The voltage across the resistor starts from maximum 5 volts and decays exponentially following capacitor's behavior, and the current flowing through the circuit is similar to the voltage across the resistor. Here is the summary for the case where T on is equal to T off is equal to 5 milliseconds. We can see how the input voltage has transformed across capacitor, resistor and how the current flowing through the circuit looks like. If time constant of the RC circuit is comparable to the input pulse width, then it will not resemble the behavior for bipolar voltage pulse train input. Thank you for watching this video.